All right, this is Horner, and let's go ahead and take a look at linear acceleration. So we know that sometimes you'll have a constant velocity, but more often than not, you're going to have an acceleration. So we always have to think about if the velocity changes from one velocity vector to another one during an interval of a time, then we can just take that velocity change and divide it by the change in time. So it's pretty simple to do if you do it this way. And whenever we want to find a acceleration vector, or how long that acceleration vector is, we can use this tactic to go through and do it. So we've got an initial velocity and a final velocity. We want to know what is the overall acceleration, or what's that change in velocity. So you can draw the two like this. Then we can flip one of them. So let's go ahead and flip the initial velocity vector, so we'll make the direction different, and then we're going to add those two together. So you can either say that you're adding or subtracting them. If you're adding them, you're adding the reciprocal of one. If you're subtracting them, that makes it a little bit easier to kind of think about. So when we do that, we see that we get a change in velocity. So that change in velocity is right here. So that tells you the direction of the acceleration. So step 3 was just to go through and do our subtraction or add the negative, and that's the direction of the acceleration. The average acceleration is going to be right here, and this is at the midpoint of the VI and VF. So you'll notice that right here, that's where our acceleration is going to be, and it's an average acceleration, okay? So it goes beside the dots, not beside the velocity vectors, so be really careful when you do that. For the next one, this one is just talking about how to think about a complete motion diagram. So when we are thinking about a complete motion diagram, you'll have to have several things within that diagram. So you can go through and kind of read what is there, but we'll take you through an example that'll use all of these steps. So this first one is you're skiing through the woods. You've got a skier glides along a smooth horizontal snow at a constant speed. So that's where we are here, and then goes down a hill and starts to speed up. So they want us to model the skier as a particle, and we can say that the downhill slope is just a straight line. So we can do that. There's no bumps or hills or moguls or anything like that on it. Alrighty, so let's go ahead and start thinking about how to do this. So we're going to visualize it. This is the complete diagram. You'll notice that the dots here are equally spaced as this person is going along. And then if you were to take the VF and add it to negative VI, you'll see that there's no change in velocity there. But if we do it down in this area where we're looking at VI and VF, and we do negative VI here, we do get an acceleration vector. And that acceleration vector is the average acceleration. And for what we're doing right now, these accelerations are going to be the same. So we call that constant acceleration, or uniform acceleration. It's not changing at all. So the difference between the first two vectors here is the acceleration, as well as the second two vectors, and those will be the same. So you can really look at it between any of the two. When an object is speeding up, we'll see that the acceleration and the velocity vectors are in the same direction. And then notice that this object is moving to the left, but it's slowing down. And so the acceleration vectors are going to be in the opposite direction of the motion. So in the letter A, notice that we are speeding up here, and in letter B, we are slowing down, but the acceleration vector is exactly the same because we're slowing down to the left. So we've traveled this way, sped up, and then we make a really sharp curve, I guess. You could think about, you just done that, and then we're going in this direction, and we're slowing down. So we're not worried about the curve, we're just worrying about what's going on here. If we think about the sign of the position, the velocity and acceleration, you'll notice that the position that we have here is to the right of the origin, but it's not moving. Here we're just left. Now, if I'm moving to the right, our Vx is going to be greater than 0. Going to the left, it is negative. Here, this is going to be positive, and this one's negative. So we want to make sure that we can determine the position, velocity, and acceleration values. So remember, we said this is going to be positive, This is going to be a negative position. This is going to be a positive velocity, negative velocity. You kind of get the hint here. Positive acceleration, and finally a negative acceleration. And the x that you see in each one of these just means along that path x. It could be y, could be z. Any of those would work. For this one, you'll notice that we are above the origin. Here we're below the origin, so positive, negative, moving up, positive, moving down, negative, and the acceleration vector points up. Here it points down, so we can do positive or negative. Now, one thing that you can do is if you define down is positive. So if you draw an arrow and say positive is down, then that would make everything the opposite. So up would be negative here. So you get to determine which direction is positive and which direction is negative. The sign of position plus or y tells us where the object is. The sign of velocity tells us in which direction it's moving. And then the sign of acceleration tells us which way the acceleration vector points. And it is not whether the object is speeding up or slowing down. So you have to be really careful when you look at acceleration vectors. So here I've got a position versus time graph down on the bottom, and you'll notice that it's looking at kind of what's happening here. So we've got an object that's moving at a constant velocity from 0 to 1 to 2 to 3 minutes, and then at 3 minutes, we notice that it travels much slower. So here is the first 3 minutes. This would be the next, and then finally the last. So this one, we're showing that you're traveling at one velocity. All of a sudden, we're traveling at a much smaller velocity, and then very quickly we change and we hit a much bigger velocity. So that's what this looks like. So we've gone from the motion diagram to the graph itself. For this one, it's just an example. It says the graph in figure 1.21a, so that's this, represents the motion of a car along a straight road. They want us to describe the motion of the car. So we've got to look at the slope. Remember, the slope of position versus time is going to tell you velocity. If it's pointing down, we're going to say it's negative. Here, there's no velocity at all, and here the velocity is positive. So in this spot, we'd actually be able to find the slope. The car is 10 kilometers to the right when it starts. The value of x decreases for 30 minutes, and that indicates that the car is moving left, or instead of saying left, you might say moving in the negative direction. And that would work out really well too. The car stops for about 10 minutes here, and then it starts to move in the positive direction. So here, moving back to the right, or we can say in the positive direction if that's the direction that we say is positive. If we're saying to the right is our positive x, and we'll say up is our positive y. The car reaches the origin again at 80 minutes. So this is just looking at position versus time, which is pretty easy to do. And that is the last slide, and taking a look at this next section.